Welcome to the deep dive. So today, we're tackling something that, yeah, it might sound a bit techy, but it's really about understanding how efficiently things get done, especially when, the amount of stuff you need to process gets really big.
Exactly, like a recipe that suddenly needs to feed 100 people instead of 4, right?
Right. Or searching for one specific email in an inbox with millions of messages. Efficiency starts to matter a lot.
And in the world of algorithms, basically, the instructions computers follow, efficiency is absolutely key. Today, we're diving into time complexity. We've got some great material here that I think explains it really clearly.
Yeah, our mission today is really to get our heads around what time complexity means without getting too lost in the weeds of complex math. We're not trying to measure the exact speed in nanoseconds.
No, definitely not. That changes all the time anyway.
Right. Depends on your computer, your phone, what else is running. Instead, we want to grasp the trend. How does the time it takes change as the job gets bigger, as the data grows?
Precisely. We'll look at concepts like constant order, where time stays flat, and linear order, where time goes up steadily with the data size, and, well, a few others too.
The goal is really to give you a practical handle on this stuff so you can appreciate why one approach might be way better than another, even if you're not a programmer yourself.
Okay, so let's start with why just timing things isn't very helpful for comparing algorithms generally. The source material makes a good point here.
Yeah, why can't we just run the code and time it with a stopwatch, essentially?
Well, think about it. The actual speed you measure depends hugely on outside factors. My new laptop versus, say, a 5-year-old machine. Totally different speeds for the same code. And the programming language makes a difference too. Some are just faster than others. Even the operating system, or like you said, other apps running, it all impacts the raw speed.
So my time and your time for the exact same algorithm could be wildly different. It doesn't tell us much about the algorithm itself, just how it ran on that machine at that moment.
Exactly. We need a way to talk about efficiency that strips away all those environmental factors and focuses purely on how the algorithm's workload scales.
Okay, so that leads us to this idea of the time growth trend instead of direct timing. Can you elaborate on what that means?
Sure. It's all about watching how the execution time behaves as the input size, let's call it n, gets bigger. Our material gives some nice simple examples. Algorithm A just prints something once.
Okay.
Doesn't matter if n is 10 or 10 million. It does one print. That's it. Its time doesn't grow with n. We call that constant order.
Like flipping a switch. One action, done. Doesn't matter how big the house is. Got it.
Got it.
What about algorithm B?
Algorithm B runs a loop in times. Inside the loop, it does something simple, like a print. So if n is 100, it loops 100 times. If n is 1,000,000, it loops 1,000,000 times.
Ah, okay. So the time taken grows directly with n. Double n, you roughly double the time.
Exactly, that's linear order. Think about reading a book more pages. N means more reading time. It scales directly.
Makes sense. Linear. Now, there was a slightly weird one, algorithm C. It was also constant order. But how?
Right. Algorithm C is interesting. It has a loop, but the loop always runs a fixed number of times. Let's say 1,000,000 times, regardless of n. Inside, it does a print.
So even if n is tiny, it still does 1,000,000 prints. And if n is huge, it still only does 1,000,000 prints.
Precisely. It might take a long time to run because 1,000,000 operations isn't trivial, but the key is its runtime doesn't change based on n. So technically, its growth trend relative to n is flat. It's constant order.
Huh. Okay. But that feels like a bit of a trap. In reality, algorithm A, one print, is way faster than algorithm C, 1,000,000 prints, even though both are constant order in this analysis.
You hit on a crucial point. Time complexity analysis, especially big O, which we'll get to, focuses on the scaling trend ends and gets very large. It often ignores constant factors or performance at small n.
So it tells you how things behave in the long run, with lots of data, but maybe not the full picture for smaller tasks.
Exactly. It assesses efficiency trends. It's simpler than direct counting, but yes, it has limitations. Those constant factors do matter in practice. But as n skyrockets, the growth trend, linear, quadratic, whatever, becomes the most important factor.
Okay, summing up this bit, we're analyzing the trend of runtime growth with input size n, not exact speeds, because trends tell us more about fundamental scalability.
Well put.
Now, the material brings in asymptotic upper bound and big O notation. Okay, deep breaths. What does that mean in plain English?
Right. It sounds more complex than it is conceptually. Asymptotic just means we're looking at what happens as n gets extremely large, approaching infinity, theoretically. Upper bound means we're describing the worst case growth rate.
Worst case.
And big O notation, written like OFN, is just the standard way to write this down. The FN part represents the growth curve, like FN, hem for constant, FNNM for linear, FNs and squared for quadratic, and so on.
So ON means in the worst case, as it gets huge, the runtime won't grow faster than a linear rate. It's like setting a speed limit for how quickly the runtime can increase.
That's a pretty good analogy, yeah. It describes the dominant growth behavior. There's a formal math definition with constant C and M, but practically we're just finding the part of the runtime calculation that grows the fastest as n increases.
Got it. Focus on the biggest, fastest growing part of the runtime equation for large N. So how do we find that big O in practice? The source mentions simplifying how we count operations.
Yes, this is the practical bit. You sort of estimate the number of operations the algorithm does in terms of n, but then because we only care about the asymptotic behavior, we simplify heavily.
Simplification rules. Love those. What are they?
Rule 1. Throw away any constant terms. If you calculate 5m plus 3 operations, that plus 3 doesn't matter when n is massive, it gets drowned out.
Okay, constants are out.
Rule 2. Drop constant coefficients. If you have 100 operations or 0.5 n operations, it's still growing linearly. The big O is just ON. The coefficient affects the actual time, but not the order of growth.
Right, the slope of the line changes, but it's still a straight line. Makes sense.
Rule 3. For nested loops, you multiply. If an outer loop runs n times, and an inner loop also runs n times for each outer iteration, you're looking at roughly nn, or n squared operations.
Okay, let's try the example from the material. Some setup steps, then a loop running n times, then a nested loop outer runs 2n times, inner runs n plus 1 times.
All right. Setup steps, constant. Ignore for big O. First loop runs n times, so contributes n.
Okay.
Nested loop. Outer is 2n, inner is n plus 1. Multiply them. 2nn plus 1 gives you 2n squared plus 2n.
So total operations roughly n from first loop plus 2n times 2 plus 2n from nested loop. Maybe add a constant for the setup, say 3. So 2n2 plus 3n plus 3.
Perfect. Now apply the rules. Drop the constant 3. You have 2n and 2 plus 3n. What's the highest power of n? It's n squared. That's the dominant term. Now drop the coefficient 2 from the 2n2 term. What's left?
Just n squared. So the big O is ON2.
You got it. That's quadratic order. The material showed how even slightly different counting, like 2n2 plus 7 plus 3 versus n2 plus n, still boils down to ON2 because that n squared term dominates everything else as n gets large.
But again, that factor of 2 we dropped does mean one ON2 algorithm could take twice as long as another ON2 algorithm in practice, right? Especially for medium M.
Absolutely. Big O gives you the scaling category, but those constant factors definitely impact real-world speed. It's a simplification, but a very useful one for understanding fundamental limits.
Okay, that calculation method seems doable. Ignore constants, ignore coefficients, keep the highest power of n. Now, we've mentioned O1, ON, ON. The material lists a whole hierarchy. Can we walk through the common ones?
Sure. It helps to see them in order, from fastest growing to slowest growing. Well, actually, let's go slowest growth, most efficient for large n, to fastest growth, least efficient.
Good idea. Start with the best.
Okay. Top of the efficiency list for large n is O1, constant time. We talked about this. Time doesn't depend on input size n, like looking up the first item in a list.
Got it.
Next, much better than linear, is O log n. Logarithmic time. This is super efficient. Runtime grows really slowly. Think binary search. You keep having the search space. Doubling n only adds one extra step.
Like searching a phone book, you don't read every name. You jump halfway, then halfway again.
Exactly. Very efficient. Then comes ON, linear time. Runtime grows directly with n, reading every page in that book, traversing a list once.
Right.
After linear, a very common one is ON log n. Linear arithmetic, sometimes called. This is where many good sorting algorithms land, like merge sort or quick sort on average. It's doing something logarithmic in time. Scales pretty well.
Better than the next one, I bet.
Usually, yes. Next up is ON2, quadratic time, our nested loop example. Comparing every item to every other item in a list starts to get noticeably slow as n increases.
Bubble sort of often ends up here.
Right. Then things get really steep. O to n, exponential time. Runtime doubles with each single increase in n. This grows incredibly fast, becomes impossible for even moderately large n, often seen in brute force searches exploring all possibilities.
Like trying every combination lock setting.
Precisely. The cell division example in the material is good too. 1 becomes 2, 2 become 4, 4 become 8, exploding growth.
Yikes. Okay, is there anything worse?
Oh yes, O(n), factorial time, n factorial. This is astronomical growth, generating all possible orderings permutations of n items. Even for small n, like 20, the number of operations is enormous. Avoid if at all possible.
Wow. Okay, so O1, O log n, O n log n, O log O n, O n. That really puts the scaling differences into perspective. Choosing an O n log n sort over an O n2 sort makes a huge difference for big lists.
A massive difference. Understanding this hierarchy is key to writing efficient code or choosing the right tool for a job involving lots of data.
All right. Now, one more layer of complexity, no pun intended. The material talks about worst, best, and average time complexity. So an algorithm doesn't always have just one complexity.
That's right. Sometimes how long an algorithm takes depends heavily on the specific arrangement of the input data, not just its size in. The classic example is searching for an item in an unsorted list.
Let's say we're looking for the number 1 in a big list of random numbers.
Okay. What's the absolute best case?
The number 1 is the very first number I look at. Found it immediately.
Exactly. How many steps did that take?
Just one.
Right. Regardless of whether the list has 10 items or a million. So the best case time complexity is O1, constant time. We use a different symbol, omega. Omega for best case, so it's omega.
Omega for best case. Now, what's the worst case?
The worst case is if the number 1 is the very last item in the list.
Or if it's not in the list at all.
Good point. In either scenario, you have to look through every single item to be sure. If there are n items, you do roughly n checks.
So the worst case is linear.
Yeah.
And we use big O for worst case, right? So ON.
Perfect. ON is the worst case time complexity. It's an upper bound. The algorithm won't take longer than linear time, no matter how the data is arranged for a given n.
So we have best case omega 1, worst case ON. What about average? What usually happens?
Good question. If the number 1 could be anywhere in the list with equal probability on average, where would you expect to find it?
Probably somewhere in the middle, like halfway through.
Exactly. On average, you'd expect to check about n2 items. For complexity analysis, we ignore the constant factor, 12, so the average case time complexity is still considered linear. We use the theta symbol for average case when the upper and lower bounds match in order, so it's theta n.
Okay, theta for average. So omega m for this search example. Why does everyone seem to talk mostly about big O, the worst case? The source mentioned it's more practical.
It often comes down to guarantees. The worst case big O tells you the absolute maximum runtime trend you can expect. It's a promise. It will never get worse than this. For many applications, especially real-time systems or critical infrastructure, knowing that upper limit is vital.
Right, you need to plan for the worst possible scenario. The best case might be rare, and the average case. Well, maybe your actual data isn't perfectly random, so the average is hard to pin down.
Precisely. Calculating a true average case can be complex, needing assumptions about data distribution. Worst case is often easier to analyze and provides that crucial performance guarantee.
And the source also clarified that sometimes people informally say average case is ON when they really mean theta.
Yeah, that happens a lot. Technically, big O is just an upper bound, while theta means it's bounded both above and below by the same growth rate, like linear. But since big O is so common, you'll often hear it used a bit loosely for the average trend, too. Just good to know the formal distinction exists.
This has been super helpful. I feel like I have a much better handle on this now. So let's try to wrap this up. Time complexity isn't about stopwatch timing.
Nope. It's about how the runtime scales or grows as the input size and increases.
And we use big O notation as a kind of shorthand for the worst case growth trend, focusing on the dominant term and ignoring constants and coefficients for that high-level view.
Exactly. It lets us compare algorithms based on their fundamental scalability.
And we saw the common types: constant, logarithmic, linear, n log n, quadratic, exponential, factorial, and how drastically different their scaling is.
Understanding that hierarchy is crucial for efficiency, especially with big data.
Plus, we learned that best, worst, and average cases can differ, but worst case, big O, is often the focus because it gives performance guarantees.
That's a great summary. It's about understanding the trends to make better choices.
It really is like that gas mileage analogy for a long trip. The MPG, the scaling, matters way more than the initial cost of a single gallon, the constant factor.
Perfect analogy. And yeah, while this covers the core of time complexity, there's always more like space complexity, how much memory is used, but this should give you a really solid foundation.
Definitely. It makes you think differently about processes, not just in code, but everywhere, which leads to our final thought.
Indeed. Here's something to ponder. Now that you have a sense of how algorithms scale, think about processes in your own life or work. How might their underlying complexity affect their efficiency as the data or scale involved grows? Are they linear, quadratic, or maybe even exponential?